Hello and welcome. My name is Vishwanath M. In this video, let us try to learn and understand a very important concept in graphs and trees called BFS and DFS, that is breadth first search and depth first search. And if you are following the VTU syllabus, this is program number 11 of Data Structures Laboratory. As usual, we will first have a brief understanding of the concept, then jump to the programming part. BFS, where B stands for breadth first search, DFS and where D stands for depth first search, have a lot of meaning in their name itself. So in BFS or breadth first search, it is we search the graph or we search the tree at a considering breadth first. So we go at a breadth first and then go deeper down the graph. So in lame words or in a different domain or in a different context, you could just consider breadth first search like touch and go. Giving a even more relatable example, if you are just visiting each module while you are studying, if you are just visiting and just then going to the next module without going to the depth of each module, you are doing a breadth first search. If you are considering each module, covering the complete depth of each module and only then going to the next module, then you are doing a depth first search, or in that matter you could call it depth first study and breadth first study. Anyway, so I hope I have made the meaning of BFS and DFS understandable by now. So in a graph, I have indicated how a breadth first search happens using the arrows, guided arrows that you see here. So as I just took the example of modules while you are studying for exam, breadth first search considers the node at each level, that is level 0, level 1 and level 2. So it considers, suppose we are starting from 0, it will go to the immediately accessible nodes, that is 1, 2 and 3. So actually it is like considering from 0, you could go to 1, you could go to 2 and you could go to 3, because you are doing a breadth first search. So after you are done visiting the directly accessible nodes, so from 0, 1, 2 and 3 are directly accessible, so you visit those 3 nodes first. Hence you would, in the output you would write something like this: from 0, 0 to 1 and then 0 to 2, 0 to 3. So the arrows that you see here is for the conceptual understanding. It goes at a layer by layer wise, or a depth level, breadth first wise. So understanding from a adjacency matrix level, we will understand what adjacency matrix is in a short time from now. But anyway, we have understood that from 0, all the directly accessible nodes are visited first. So 0, 1, 2, 3. So that is written here. So it's like you have covered each module at a high level, or at a touch and go level, or at a broad level. Afterwards, from each of the visited nodes, that is 1, 2 and 3, you visit further down the tree or further down the graph. So from 1, you would then visit the directly accessible nodes. So analyzing the output here, from 0 it is 1, 2 and 3 at a direct level. From 1 it is 4 and 5, so you write 0, 1, 2, 3. Then from 1 it is 4 and 5. From 2 it is 6. From 3 it is 7. So that is how the output of BFS can be found out. Depth first search, on the other hand, is going depth or going in detail. So if you are starting from node 0, you first visit the first accessible node. Suppose you visit 1, then you make sure that you are visiting all the visitable nodes from 1. So if you visit 1 first, from 1 you could visit 4 and 5. So hence the output 0 to 1, 1 to 4 and 5. And once you are done analyzing at a depth of one node, then you go to the next. So from 2 you write 2 and then go deeper down the graph. So 2 comma 6. Once the second branch is done, we go to the third branch, 3, and we go deeper down the tree. Hence we come up with 3, 7. So the same. So both of these are same graphs, but BFS and DFS would give different outputs, because in BFS we go at a broader level, or here if you consider layer by layer or level by level. In depth first search you go at depth, so you consider the first branch, go to the depth, come back, go to the second branch, go to the depth, and then go to the third branch from a deeper level. So hope you are able to understand how the output is written here from a conceptual understanding perspective. So we understood what BFS and DFS is. So you might think that these looks like graphs, but how they look like, you know, trees, but how are they graphs? So please note, every tree is a graph. The reverse may not be true. So every tree is a graph. So that is a basic understanding of BFS and DFS. So let us now jump into the program. We will understand these remaining part of the image later as we go down the program. Okay, so one very important understanding, or you could keep this in mind, in breadth first search, as we just saw, from 0 we visit 1, 2, 3. So it's like you are considering this as a queue, right? Even just imagining a queue here would make it easy to understand. So we from 0 we visit 1, 2 and 3, so it's like a queue. Then we pick the first node, that is 1, and then we visit the sub queue of 1, that is all the visitable nodes from 1, and then all the visitable nodes from 6, all the from 2, all the visitable nodes from 3. So by this you would have understood that in BFS we use the concept of queues. So we if you are following all the lab program videos that is present in the playlist, you would by now have understood what queue and stack means. So queue is a last in first out data structure. So in queue you would need two variables, that is f and r, or indicating front and rear. So having this understanding would make writing the program easier. Whereas in a depth first search, we you could see that this is the whole thing like this is a stack, because we are going down the graph. So we are going deeper down the graph, so it is a stack. So we visit 1, then we visit it is like a stack, we go down the stack and we visit 4. So that is a clue indicating that in DFS we use stacks, and for stack we know that the only variable required is top, and hence you would see the variable top here. So having BFS and DFS understanding as a background, now let us come to the code. stdio or stdlib.h to header files. So these are the global variables that we need in the program. Int a of 50, 50 or 50 of 50. This is a two-dimensional array. What does A mean? A means a adjacency matrix. So on paper we could draw a graph or a tree like this using arrow marks, but to represent it in the form of an array, in the form of a two-dimensional array, this is the representation we will have to use. So we will understand how to write an adjacency matrix for a graph later in the video, but know that we are creating a adjacency matrix of 50. Just to be on the safer side, we are creating a large enough adjacency matrix. Then n indicates the n indicates the number of vertices in the graph, and we are creating two arrays, b visited and d visited. B visited indicates visited matrix or visited array, while we are doing a breadth first search. B stands for breadth, and d visited is the same when we are doing a depth first search. So the idea of using two visited arrays is, in the main function we can while having entered just one graph, we can do both BFS and DFS and see how the output varies. So that is the idea here. B visited and D visited of 50. Alright, so now always have a conceptual understanding first and then write the program. So we know that for BFS we need a queue, so we are creating a queue. Again you could create a queue of 50 size if required, but otherwise 20 is large enough. So int queue of 20, and in queue we need front and rear variables, both initialized to -1. In a stack what we need is again for stack we are creating another array s of 20, and what we need is top. We may not use the variable count, but let us have it declared here. If we are not using it anyway, we can delete later down the program. So we have understood adjacency matrix, number of vertices, b visited and d visited for respective search methods, queue and stack for respective concepts again. So queue will be used in BFS, stack will be used in DFS. So let us now, we know how BFS works, now let us see how it is done in a code. void BFS int v. So what is v? V is the starting node, or what you could consider as the first visited node. Suppose you want to start your search from 0, then you would have to pass the value of v to be 0. In this case, if you are starting from 1, you would have to pass the value of v as 1. So int I is a iterary variable. CUR is a current. We will understand why it is required. So since we are doing a BFS, we are using b visited array, and so visited array, I have defined it here. Visited array is used to keep a check on all the visited nodes. So whichever node you start with, that node is visited, or that node is visitable. So we make that as 1. Moving further, since we are using a queue in the queue concept in BFS, we know that addition or insertion happens at a rare end. So queue of plus plus rare. So this is a pre-increment. That is so in a BFS, you know that the rare will have to get incremented as we keep inserting new elements into the array. So that is what is done here. Q of plus plus rare is equals to v, where v is the visited node or the starting node, while front is not equals to rare. So when do we know what is the concept behind this front is not equals to rare? We know that we are considering a queue of all the first directly visitable nodes, or the queue of the directly accessible nodes. So while front is not equals to rare, we consider each element in the queue. So we do a dequeue operation here. So how do we delete or remove an element from the queue? We use the front variable. So front has to be moved forward. So queue of plus plus front, whatever is there in the firstmost node in the queue, firstmost element in the queue will be stored in current, and using current we go down the graph. So for I is equals to 1, I smaller than n, I plus plus, if A of current of I, what is A of current of I? A is basically the adjacency matrix, and we know that current is the starting the starting accessible element in the queue. A of current of I is equals to 1. So what does 1 indicate? So it is now that we need to understand what adjacency matrix is. So forget directed and undirected graph. So what basically adjacency matrix is it is a matrix or a two-dimensional array used to represent any graph. The only difference between directed and undirected graphs is, in directed graphs the arrow mark between the nodes are having an arrowhead, whereas in undirected graph that it is headless, or the arrow doesn't have a head. So what does the arrow indicate? From 1 we could go to 2, but this arrow mark indicates that from 2 we cannot go back to 1. That is the meaning. Whereas in an undirected graph, if there is a line, if there is a connection between 1 and 2, that means from 1 could go to 2, and from 2 one could go back to 1 again. So that is the meaning of directed and undirected graphs. All this is not very important for this program in particular, but it is better to understand this concept, because all of this is related to graphs and trees. So let us consider this example from now on. Undirected graph you could consider if you are interested to go deeper down these, go at a depth of this program. So directed graphs. So from 1 we could go to 2. How do we represent that? So adjacency matrix. So basically imagine that this two-dimensional array, each of them each element in this adjacency matrix indicates the possible connections. So from 1 we start from 1, and by default if we understand the main function, if we see the main function, we know or we understand that the adjacency matrix is by default always initialized to 0, but anyway we could just have that in mind and then understand what adjacency matrix does in the program. So from 1 we are connecting to 2, so hence from in the row indicating 1 and the column indicating 2, we place 1. That means 1 to 2 is possible. And from 1 we have an arrow to 4, so that means from 1 to 4 we indicate 1. Moving ahead, from 2 we have an arrow to 3, so from 2 we have an arrow to 3, so place a 1 there. For 3 we have an arrow to 4, we don't have any other arrows, so for all the others you have to put 0, and for 4 you put 1. And in 4 you would see that there is no arrow mark going out of 4. That means from 4 you could not go anywhere, but from other nodes you could probably come to 4. That is why for 4 you would have all of them as 0. So just to identify the difference, in an undirected graph we see this arrow mark, we see this arrow between 1 and 2. That means from 1 to 2 is possible, 2 to 1 is also possible. That is why 1 and 2 there is a 1, and 2 and 1 there also there is a 1. Anyway, let us not confuse by considering undirected graph now, but only consider directed graph for this program. So why I explained all this is in the BFS, that is breadth first search, how do we know that there is a connection between 0 and 1? There should be a value of 1 in the adjacency matrix. So we do that comparison or check in this if construct. If A of current of I is equals to 1 and B of visited of I is 0. That means initially we don't know what is visited and what can be visited, so all of them will be 0. So if the visited array, that is an array which will keep a check on what is visitable or what is visited, if it is 0, but if it can be actually visited or if it actually can be reachable, what we do, you enter the if construct, you see that to the queue you add the element, whatever is the element that we just saw. So from 1 we saw that from 1 to 2 is possible, so you add the element 2, that is the second, that is column value, to the queue, that is adding to the set of all elements visitable from 0, and then we saw that before visiting it will be 0, but after visiting we make the respective value as 1, B of visited of I will be 1, and then we print a %d I, that was from 0 what are all the nodes visitable or what are all the nodes that is possible to visit. So I hope I have made the understanding of BFS clear. So BFS works on the concept of queues, and queue will have obviously two variables called front and rear. We use this array called visited to keep a check on what is visited and what is visitable. We use the concept of adjacency matrix, and wherever there is a 1 in an adjacency matrix, that indicates this row to column is possible. Row number 1, that is element number 1 to element number 2 is possible, that is the traversal is possible or there is a path. So that is the understanding of BFS. So always have this conceptual understanding. We go broader level or layer by layer or level by level in BFS. The implementation of DFS is relatively easy because we are using a stack, and in stack we know that insertion and deletion happens at the same end. So and we are also using the concept of recursion. So understanding DFS is writing the program of DFS is actually simpler because the number of lines is lesser, and we are using the concept of stack. Anyway, so the function prototype is remain the same, void DFS int v, where v is the starting node or the node that we want to start the search from, and d visited of v. So wherever we start, suppose we start with 0, we make sure that that is visitable or that is visited. That is making total sense, so it is obvious. S of plus plus top, since we are in the DFS we use the concept of stacks which has only one variable or pointer. S of plus plus top is equals to v, that is we insert what is the element that is visited, and then we run this for loop. So you would probably see the similarity from here. There is a for loop and for loop. So what happens inside the for loop is also very similar. If a of v of I, so here we are using this variable called current to access this access each element from the queue, because if you see here we first know that 0 1 0 to 1 2 3 is possible, but again we have to take this queue and then start from the first element of the queue. That is why we need an extra variable called current. Whereas in DFS we know that once we take the value 1, that is once from 0 we know that 1 is visitable, we will explore all the paths of 1. So we don't really need a extra variable called current. That is the difference in DFS. If A of A again is adjacency matrix, V of I. So what is V? V is wherever we start initially, that is suppose you are starting from 0, or if you are starting from 1 here in this case, A of 1. What is A of 1 and I? I always starts from 1, so we start from here. So wherever there is 1 and if the D visited, so the logic here is same. D visited is for the DFS search, it indicates what element is accessible or visitable. So if it is 0, that is before visiting it will be 0 obviously. So what we do, we print that it could be visitable or it is accessible by DFS. And as I said, DFS is a recursive program, so a recursive function. So as I said, recursive function means the function should call itself. So once understanding is from 0 we visit 1, and then whatever we did here, that is from 0 we came down to 1, so we have to go down the stack. So that is we are doing the same thing, that is we are doing a recursion, and hence we are calling DFS of I. But what is I here? It will automatically get incremented each time in the for loop. So it will, even if we start with 0, it would be 1, then it would be 4, things like that. So that is the concept of DFS. So we are now only left with the main function. A main function is actually very simple. We are just creating a choice or a menu for the different choices we have. Anyway, we have the different integer variables, ch indicating the choice, start indicating where we start from, I and j are the iterary variables. Alright, so printf enter the number of vertices in the graph. So if this is the graph, we have to create a similar adjacency matrix. So we ask for the number of vertices and take that input as n. And then printf enter the adjacency matrix. So how will the user, suppose if this image is drawn on the board and you are asked to implement BFS and DFS, you have to first write the adjacency matrix using the logic I have already explained, and then enter the adjacency matrix in the program here. Enter the adjacency matrix. So for I is equals to 1, so we start with 1, not 0 as the normal convention. We start with 1 because the first the node, the element or the node in the graph could be 1, so it will not normally start with 0. So for that purpose, to have the understanding easy, we will use this convention of I is equals to 1, I smaller than equals to n, I plus plus. So since this is a 2-dimensional array, we need 2 for loops for each row, and for each column we are taking an input, scanf %d and of aij. So these are all basics of arrays. This is how we take the input for a 2-dimensional array. We have now accepted the input for adjacency matrix. So as I said earlier in the program, visited of I initially, the whole thing will be 0, because before we start BFS or DFS, we want the visitable or visited nodes to be 0. So how do we do that? We run a single for loop and initialize both the arrays to 0. So this is clear. And since we are doing a BFS and DFS, we want where the starting vertex should be, from where should we start the search from. So printf enter the starting vertex and we take the input as start. After having done this, we can have a while loop which is an infinite loop, and then have these 2 options or these 2 choices for the user. Printf menu, enter 1 for BFS, 2 for DFS, and 3 for exit. And depending on the choice, we will take the input, enter your choice, scanf %d and ch. Based on the choice, we run the switch construct. In the switch construct, case 1, node switchable from vertex whatever is entered as the starting node from that start node R, we call BFS function. This is understandable and it is obvious because 1 stands for BFS, and we pass start as the parameter. So case 1 will break here. The same goes with case 2. We call DFS function and we break after execution. If the choice is number 3, we will exit the execution of program. So if there is any other input that the user enters by mistake, we want to print this message by default, enter a valid choice. So main function was easy and not really too challenging. So we have understood the concept of BFS and DFS. This is a relatively smaller program than the other programs, but conceptually one should have a complete or sound understanding of what BFS and DFS means, what directed and undirected graphs means, what is the meaning of adjacency matrix, and what is how we write an adjacency matrix from a graph. And one should also have in mind that in BFS we use the concept of queues, and in DFS we use the concept of stacks. And we know that we are using a visited array to keep a check on all the visited nodes. So that was the summary of the theory or explanation. So now let us jump to the execution part. So here we start with execution. So we know how to execute a program using GCC compiler, GCC p11.c. So because the program name is p11, that is what we have saved. If there are no errors, the cursor will blink in the next line indicating there are no errors in the program. And how to execute a program using /a.out. enter the number of vertices in the graph. So know that something like this would be asked or would be given on the board for you to understand and execute the program. So how many vertices are present in this? There are 4 vertices. Please understand that for any graph we can create a adjacency matrix, but more complex the graph or the tree is, the larger will be the adjacency matrix. So always remember how many ever nodes are there, that that number of 2 cross 2 matrix has to be created. So in this case I am considering this for execution. Number of vertices is 4. I click 4 and enter the adjacency matrix. So looking here, I would enter the adjacency matrix 0. So how you would enter an adjacency matrix is just the way it appears: 0 space 1 space 0 space 1. You have completed the first row. You could continue in the same line, but for our understanding you could click enter and then come to the second row: 0 0 1 and 0. Third row is 0 0 0 1 0 0 0 1, and fourth row is 0 0 0 0. I hope writing the adjacency matrix is clear by now. If just to have a very quick recap, how did we come up with this adjacency matrix? So from 1, the first step is create a adjacency matrix, that is draw a box like this, and how many ever nodes, 1 2 3 4, creates so many rows, 1 2 3 4 and so many columns. After that, the first step should be forget the zeros first populate the ones. So from 1 you see an arrow towards 2 and then you see an arrow towards 4. So in row number 1 write 1 under 2 and 4. Next go to 2. From 2 you have an arrow towards 3. So just go to 3 and write a 1. From 3 you have an arrow towards 4. So just under row 3 column 4 write 1. And from 4 you don't have any outward going arrows. That means from 4 you cannot actually visit any node. That means just don't do anything. So after you have completed writing the ones, just fill up zeros in all the other positions. I hope I have made writing an adjacency matrix clear and easy. So after you have written the adjacency matrix, enter that here and click enter. Starting vertex. So starting vertex is important because where do we want to start the search? So in this program, so let us first start with 1. So before we actually see the output, so I will first explain how will be the output. So from 1, if we are doing a BFS, we will see an output like maybe 4, 2 and then 3, or maybe we may have 2, 4 and then 3, because going back to this level, so or this perception, from 0 what are all the nodes visitable, from 1 what are all the nodes visitable, it is 4 and 2, it could be 2 4 or 4 2, but doesn't matter. But we are not going down the graph or the tree here in the BFS, because from 1 we don't go to 2 and then go to 3 without visiting 4. So that's the only difference. Whereas in DFS, if you visit 2 first, the next output will be 3 and only then we will have 4. Anyway, we will see that output in the execution screen. So starting vertex is 1. It asks for the menu. So let us now first see 1. So I click 1 and hit enter. Nodes reachable from vertex 1 are 2, 4, 3. So as I just said, so from 1 you can visit 2, you can visit 4, the first directly accessible nodes. So if you have followed the explanation, this output you will be able to validate that it is correct. So from 1 you are able to visit 2 and 4, then we go down to 3. That is what happens here. So for the same graph, let me now run a DFS search. So for DFS my choice would be 2. So as expected, so from 1 if you visit 2, immediately it will next visit 3, because in a DFS it will go deep down the graph. So it will be 1, 2, 3 and then 4. So let us now see if the output is just the same. There we go. From 1 the output is from 1 it could go to 2, then 3 and then 4 is being printed. So I hope writing this program and then correlating the concept and validating the correctness of the program in the execution is now possible. So we are now left with the last choice to gracefully exit the program and end the execution. So there we go, we have completed the execution of BFS and DFS. In this video you have understood the concepts, you have learned how to write the program and also how to execute the program. That was all in this video. Thank you.